So we've had our introduction to the complex exponential function. And we've looked at it from an arithmetic perspective. We know what its real and its imaginary parts are, and it allows us to compute things like e to the power I. Right? What we're trying to do now is take that a step further and figure out, now that we know what the complex exponential function does, how/can we undo what it does? Does the complex exponential function have an inverse? Now, when we studied the exponential function f of x equals e to the x as a function with a real input and a real output in the high school curriculum, it's a really friendly function. It's one-to-one, and it is onto all positive outputs. Right? So there are no two real numbers that have the same exponential, and every single positive real number is the exponential of something. And so we can define an inverse in high school for the exponential function that we call the natural log function. And we can take the natural log of any positive number and get a real number out of that. So what changes and what remains the same when we think about the complex exponential function and its inverse, which we might like to call a complex natural logarithm? So to get to an answer to that question, let's just quickly remind ourselves about how we define the complex exponential function. We used Euler's identity to come up with this formal definition that e to the power z, e to the power x plus iy, is e to the x times cosine of y plus I times e to the x sine y. And so having the rectangular expression of the input makes the real and imaginary parts of the output the most comprehensible. So we'd like to know how to go backwards. What might a complex logarithmic function look like? So the first question, anytime we want to try to find an inverse function in any context, we have to ask whether the original function, in this case the complex exponential function, is that original function even invertible to begin with, or are we on a fool's errand somehow? So let's try and determine whether or not f of z equals e to the z, the complex exponential as we've defined it, is a one-to-one function, and whether it's an onto function. And remember, it needs to be both of those things before we can have an inverse function for it. So to figure out some of those properties, the one-to-oneness and the onto-ness, I want to take a moment and look at the mapping properties. What does the complex exponential function look like as a transformation of the complex plane? So here we are in the complex plane, and I've put the polar coordinate grid on top of the complex plane for reasons that I hope will become obvious pretty shortly. So in order to wrap our heads around the mapping properties of the complex exponential function, in my mind, the easiest way to do that is to look at what this mapping does to vertical lines in the domain and what this mapping does to horizontal lines in the domain. And also, just for fun, let's start out by looking at what this mapping does to a ray drawn through the origin. So if I draw a ray through the origin of the complex plane, and then I apply the exponential function, the complex exponential function as we have defined it, to this ray, what am I going to get? Well, I end up getting this curve. This curve that kind of, it spirals in towards the origin on one end, and it spirals out towards infinity on the other end. And as I vary the angle of this ray through the origin, the spiral has kind of a different pitch. It either gets sort of narrower or wider. And the closer that this original ray gets to vertical, the more that that image under the exponential function kind of looks like a circle. And the closer that this ray gets to horizontal, the more that it looks like that image is no longer a spiral, but in fact a straight line emanating from the origin. Hang on to those observations. But this observation that a ray that's neither horizontal nor vertical, so an oblique ray through the origin, its image under the complex exponential function is a spiral, in fact it's what we call a logarithmic spiral, is actually the source of one of the great applications for this complex exponential function that we'll talk about in the next video. So to make things a little bit more understandable, let's, instead of a ray through the origin, let's think vertical lines and horizontal lines. This is very often the easiest way to understand what a complex function mapping is doing, is to kind of ask, what does it do to the grid on my rectangular graph paper? Let's start with horizontal lines. So if I have a horizontal line in my domain somewhere, and I apply the complex exponential function to it, what I notice is that horizontal lines at different heights seem to be giving me segments of a ray emanating from the origin that are sort of emanating at different angles from the origin. So somehow the y coordinates of my points are becoming the angles in the image under the exponential function. So y coordinates are somehow turning into angles. Hang on to that. And as I choose different x coordinates, so as I make this horizontal line segment shorter or longer, it looks like I just get more or less of that ray that's going into or out of the origin. So maybe somehow my x coordinates are telling me something about how far away from the origin that we are. So there is important observation number one, is that I think we've already talked our way into the idea that vertical coordinates, so y coordinates in the domain, turn into angles in the range, and that x coordinates in the domain turn into moduli, distance from the origin, in the range. Let's see if we see that same kind of thing happening if instead of looking at the images of horizontal lines, we look at the images of vertical lines. So here's a vertical line segment somewhere in my domain of my complex exponential function, and here is the image of that line segment. Oops, looks like it's a little too far out. Let me scoot this in a little bit. So there is the image of this vertical line segment. And since we have a polar coordinate grid in this graph, you might be very tempted to say, actually, it looks like that image is a portion of a circle centered at the origin. So somehow this exponential mapping turns vertical lines in the domain into circles in the range. And as I choose different x coordinates, the radius of that circle gets bigger or smaller accordingly. This would be further confirmation of the observation that we made a minute ago, that somehow x coordinate determines how far away from the origin that you are in the range, and the y coordinate in the domain determines what angle you're making with the positive real axis in the range. And another really important feature of this mapping, if we go back to the question that we were asking, the question that we're asking is the complex exponential function even one-to-one? Because if it's not, then we're going to have to work a little bit harder to determine an inverse for it. There may still be a way to salvage an inverse, but we need an invertible function to be one-to-one on its domain and onto its range. And from this example, I think we can convince ourselves fairly quickly, if I extend this line segment in the domain far enough, that this circle actually wraps back around in on itself, so that both the top point on this line segment and the bottom point on this line segment in the domain are both getting mapped in the codomain, the range, to the same point. And therefore, I think we are ready to say to ourselves that, in general, the exponential function does not look like it is one-to-one on the complex plane, because the top point on this line segment and the bottom point on this line segment are both getting mapped to the same image point in the range. Let's see if we can verify that hunch using arithmetic. So the complex exponential function turns out not to be one-to-one. And one of the most important reasons that it's not one-to-one is that if I have two complex numbers that differ by 2 pi times I, in other words, in the complex plane, two complex numbers that are separated by a vertical distance of 2 pi I. So it looks like the top point on this line segment over here is at a y-coordinate of pi, and the bottom point is at a y-coordinate of minus pi. So they are separated by 2 pi times I, 2 pi in the vertical direction in the complex plane. We can check that two such complex numbers are going to have the same exponential. They're going to land on the same image point after we process them through the exponential function. That's because e to the 2 pi I is cosine of 2 pi plus I times the sine of 2 pi, but the cosine of 2 pi is 1 and the sine of 2 pi is 0. So e to the 2 pi I is just equal to 1. So e to the z plus 2 pi I is indistinguishable from e to the z times 1, in other words, e to the z. So for any complex number z, both z and z plus 2 pi I are going to have the same image under the exponential function. So not only is the exponential function not one-to-one, it's a periodic function. It's 2 pi I periodic. Because if z and z plus 2 pi I have the same image, that means that z plus 2 pi I and z plus 2 pi I again, z plus 4 pi I, also has the same image as those two. And z minus 2 pi I has the same image as them, and so on and so forth. So because the Euler identity forces us to define the exponential function in terms of sines and cosines, and those sines and cosines are 2 pi periodic. That means that the complex exponential function inherits a 2 pi I periodicity. So not only does the exponential function fail to be one-to-one, it fails infinitely often. Right? There's a whole infinitude of different points in the domain of the complex plane that all land in the same spot after we run them through the exponential function. So they fail to be one-to-one in the same way that the sine and cosine function in high school fail to be one-to-one. They fail the horizontal line test infinitely many times. Same kind of thing is happening here. It's just that the period of the complex exponential function is an imaginary period, 2 pi I. That's why when we were just looking at the real version, we were just looking at what this function does on the real axis, we didn't notice that it was not one-to-one because it was one-to-one on the real axis. But once we expand our vision into the complex plane, now we have a 2 pi I periodicity that makes the complex exponential function very much not one-to-one. But that's not the end of the story. We still, one of the big things that we learned in our previous week's investigations is that we can still salvage the invertibility of a function that's many-to-one. We just have to first restrict that function to a domain on which it is one-to-one. So what might that look like if we were to do it with the exponential function? So the best way to do that I know of, is to define what we might call the principal exponential function. The principal exponential function is going to be the one which correlates to the principal branch of its inverse, which is going to be defined in terms of the principal argument of a complex number. So we're using the word principal kind of in a way to line up all of our different usages of that word so far. So how we can find a domain on which the complex exponential function is one-to-one, we just have to make sure that this 2 pi I periodicity doesn't bite us in the behind. We just need to make sure that any two complex numbers in my domain cannot, in fact, be separated by a vertical distance of 2 pi. And one natural way to do that is to just take the horizontal strip in the complex plane, which runs from the imaginary part of minus pi up to the imaginary part of pi. If I do that, then no two z's in that domain are separated by 2 pi I. Right? The maximum amount of vertical separation is 2 pi I within there is 2 pi within this strip, but I'm including only the top horizontal line and not the bottom horizontal line as part of that domain. So if we were to visualize this, which I think always helps, the domain we're talking about is this horizontal strip. Right? So all of the inputs to my complex exponential function when I'm using the principal exponential are going to be taken from this strip. We're including the top border, but we're not including the bottom border. We're also letting this strip extend infinitely far out to the left and to the right. And again, one reason that we might want to do that is that the x-coordinate seems to determine for us sort of how far away from the origin that we are. And so as x approaches 0, it looks like we end up in the image being a distance of 1 from the origin. As x goes to minus infinity, we are a smaller and smaller distance from the origin that sort of converges towards 0. As x goes to positive infinity, then our distance from the origin in the image seems to go out to positive infinity. So we can still have a one-to-one function that doesn't matter how many x's, how many x-coordinates that we choose, because as we sweep x from minus infinity to positive infinity, we sort of get all possible distances to the origin. But in order to get all possible angles without repeating any angles, we can't let the points in our domain be separated by more than 2 pi, because then the periodicity is going to make this not a one-to-one function. And so the way to get the maximal amount of image out of this function is to stop right at the horizon where we would have points separated by 2 pi I by including the vertical coordinate of pi, but not including the vertical coordinate of minus pi. So we have a 2 pi width or 2 pi height strip of the complex plane, which forms the domain of our principal exponential function. And on this domain, the complex exponential function is one-to-one. It's also true that on that domain, it is almost an onto function as well. And here's an algebraic demonstration for why that might be. If I take any non-zero complex number w, and if I write it in its polar form, r angle theta, can I solve the equation w equals f of z? If I can solve that equation for every such w, then that means that every such w is part of the image, part of the range of my function. So can we solve w equals f of z? Well, w is r angle theta, that's r cosine theta plus I times r sine theta. Meanwhile, f of z, the exponential function, is e to the x cosine y plus I times e to the x sine y. Factor out the r on the left-hand side and the e to the x on the right-hand side, and we find out that as long as our z is taken from this domain that we've defined, that means that there is one and only one solution to this equation. That is to take r equal to e to the x and theta equal to y. So that theta ends up being the principal argument of w. And so each of those equations could then be turned around. Might as well type this in here because I forgot to include it in the notes. Each of these could then be turned around so that x is equal to the natural log of r. Again, if r is e to the x and both of those are real numbers, then that means that we're good. So if I'm trying to determine what is the x-coordinate of a point which maps onto r angle theta, that x-coordinate is the natural log of the r, the modulus, the distance to the origin. And if I know the principal argument of what I'm putting into this function, then I also know the vertical coordinate. So if you tell me the r and theta of w, I can figure out what were the x and the y of the z for which e to the z is equal to w. So any non-zero w, this will work. But the case of w equals 0 is the only one that we cannot solve. Because in order to solve 0 equals e to the z, we would need to have a 0 radius, a 0 modulus. R would have to be 0. But we cannot solve 0 equals e to the x for a real number x. Because there is no real x for which e to the x is equal to 0. E to the x is always a strictly positive quantity for any real number x. So the principal exponential function is almost onto the entire complex plane. It's in fact, its range is all non-zero complex numbers. So it's the complex plane punctured at the origin. So finally, 17 minutes in, we're going to define the inverse of the principal exponential function. Now that that function is one-to-one and onto the punctured complex plane, we can define its inverse. And its inverse is what we call the principal logarithm function. We're going to denote it by log z, so always log and not ln, because we're going to use ln for the real valued function that's familiar from high school. And we use a capital L to indicate we're using the principal branch that's giving us the principal argument of the inputs. And so we can just define it according to what I just sort of typed up here. Right? We can define it by having its real part be the natural log of r, natural log of the modulus of the input, and its imaginary part is just the principal argument of the input. So where the complex exponential function was best understood using the rectangular form of the input, the principal logarithm function, which is the inverse of the principal exponential, is best understood when we express its input in polar form. So finally, let's use the principal logarithm function to come up with an application. Let's revisit the question of how we might raise I to the power I. So now that we know how to compute the principal log of I, that's going to allow us to change base from a non-real base I into a real base, which is e, which is going to allow us to use Euler's identity. So how would we find the principal logarithm of the complex number I? Well, we would just have to write I in its polar form. In its polar form, I is 1 angle pi over 2. Its modulus, I, is a distance of 1 away from the origin. And its principal argument, because it's on the positive imaginary axis, it makes a right angle with the positive real axis, so pi over 2 radians. So I is 1 angle pi over 2, and therefore its logarithm, according to our formula, has real part equal to the natural log of the modulus, so the natural log of 1. But the natural log of 1 in high school is 0. And that's what ln means, right? Meanwhile, the imaginary part of the log of I is the principal argument of I, and the principal argument of I is pi over 2. So the principal logarithm of I is equal to I times pi over 2. And now that we know that, we can compute what is I to the power I. I to the power I, we can just change base. So rewriting the base I as e to the principal log of I, because again, here e to the something is the complex exponential function, and capital L log is the principal complex logarithm. But the principal complex log of I, we decided was I pi over 2. So this is e to the I pi over 2 raised to the power I. and taking a power to a power leads to the multiplication of those exponents. So here we're going to get e to the I squared times pi over 2. But I squared being -1, we get that this is equal to e to the minus pi over 2. And one of the surprises is that we ended up getting a real number as the output of I to the power I. So that's what we can do with the complex exponential and complex logarithm functions. In the next video, I want to talk just a little bit about an application. This is worth sticking around for because it may give you some ideas for how you might bring these ideas about the exponential function as a mapping into contexts where maybe you're not trying to learn complex variable analysis, but which might end up being engaging for students at the middle and high school level. So stick around for the next one.